Hello, I'm here to present the project Opti-Ori by the team MaPSY, which was composed of Sam, Michael, Yufeng, and Peter. Orienteering is an adventure hiking sport which participants race between a series of checkpoints in unfamiliar territory with only the aid of a compass and map. An example of a map can be seen on the right, which helps give the participant knowledge about the surrounding terrain. Key things to note is that checkpoints are highlighted in purple, and different terrain features are represented with different colors and/or textures, such as representing dark forests or marshes. Elevation changes can then be represented through a series of contour lines. An example trajectory for the map shown can be seen here, and one can see that it is a delicate balancing act between minimizing one's path while also navigating between different features. One can quickly realize that this is very similar to a path planning problem, which there are many optimal algorithms. This motivates the problem of how do we go about interpreting these orienteering maps so that optimal path planning algorithms such as A* can be used to find routes. To do this, we first had to go about segmenting the lines out of these maps, and for this we developed our own algorithm. First, the user goes about selecting a color on the map which corresponds to a pixel which matches the featured line's color perfectly. From this, we then add this color to a unique color array, and then we iterate over, checking which colors are in the map are similar to this unique color array and expanding the unique color array accordingly, and then checking all of the adjacent pixels we have determined to be part of the line and evaluating their respective color as well. This helps these lines to go with respect to color as well as spatial proximity to previously determined line segments. One can see that on the first iteration, when there are only three unique colors selected, we have this original scope of these respecting line features. As we go about iterating through the problem, we increase the size of our unique color array and grow which colors and pixels are represented as lines. By the fourth iteration, you can see that we've well represented and captured the contours from this map. From this, we can also use this to pull out the trajectories of paths, the route itself, and all of the contours. And this then feeds into the second part of the problem. First, we go about cleaning the map. This is useful as it removes these lines which may prevent occlusions when it comes to segmenting the map by these different terrain features. With this cleaned map, we can then go about filtering it to take any textured regions and turn them into a uniform color and clean up any residual pixels. From this, we can then do a superpixel segmentation to find the boundaries between the different likewise regions and then classify them against predetermined colors which relate to the differing regions. From this, we can then transpose the map of the paths to get a cost when it comes to the different terrains, and we can take our contour features to represent elevation cost and add them together to find a cost landscape for the given map. Using this cost landscape, we can then go about running A*'s path planning algorithm to find an optimal route, and for this case we found that it was comparable to the fastest route for a human on this map.